details how to process diffusion data and how to go from, well, I hope that you know how to go from DICOM to Nifty with DICOM to Nifty X. So this is already, I'm not going to explain that. I'm going to give a quick overview again about the preprocessing pipeline. As basically, I'm starting where Agma finished last time, but essentially it's the same thing. So I think he did a already good job presenting that. And I'm pointing here some of the resource you can find for your analysis. Okay, so if you go on the website mblresearch.github.io, you will basically, this is our new home for the lab. And here we're going to put all the tools we are going to make available. We will make a lot of more tools. We just kind of migrated now recently. Here there will be, let's go and see actually what is there. So we have already Startrack is already there, the latest version. MBL tools. MBL tools, in reality, is a sort of a collection of all the script and tool from our lab. There are a lot of stuff. It's currently a chaos, so we haven't released everything in one go. So in the MBL tools, you can find now all the preprocessing pipeline. So I think it's the main priority is for people to get the preprocessing sorted. Over time, we're going to put some, I don't know, stuff, for example, how to do operation between streamline and surface with FreeSurfer, or how to do some kind of calculating some SNR map, removing some gradient table, removing some data example. So there are a lot of nice, useful tools that you don't want to rewrite it yourself. So we have been using for the last, 15 years, these two MBL tools. And we're going to make available these utilities also for you. But for now, in MBL tools, essentially is the preprocessing pipeline that Hagman talked about. So if you go here, you can have two different ways of installation. So if you have a Windows or a Linux machine, my suggestion, if you really want to do a full proper installation, you can have a native installation. So you can install a different library, the different dependency. So it normally is FSL, ANS, Tortoise for some denoising keeps ringing. If you have that in your bash path, then just install this kind of script as well in the path and everything is ready to go. If you have no idea what I'm talking about, just download the Docker desktop app, and then you just have one command to run, and automatically it will install and run for you the preprocessor without installing any dependency. So this, for example, let me see. I wrote the page. I already forgot what I wrote. Let me see what I'm saying here. Yeah, as I say, can you see? Can I get it bigger? Sorry. Just a second. Let me try to get the. Okay, now a little bit bigger so we can see better. Okay, so right. So we have two options. Can go native installation, so install the tools and the dependency. It could be Linux, Windows, Linux subsystem, macOS, etc. That's what I've done for my laptop. I've installed exactly all the dependency and it's fine. But if you prefer to have a much more kind of flexible installation for Linux and Windows, I suggest to probably you want to install Docker desktop, and then I'll show you down there is an option for how to install everything, and that's it. Then you literally have to run all with the option, and the preprocessor is running. So what we are doing in the preprocess, if you remember what Ahmad showed the other day, this is kind of the order logic. We are doing denoising, we're doing Gibbs ringing, we are doing masking using OptiBet, we are doing top up, we are doing eddy current motion correction, and finally we also do a quality control. Quality control is quite useful. We haven't had it yet, but we also have a script to generate a nice spreadsheet at the end. When you run, for example, 100 subjects on the subject, you don't want to go back check one subject at a time to see if it's good or bad. We have a nice spreadsheet that's telling you what is the SNR, what is the artifact, what is immediately see. You can do it, with the filter in Excel. You can sort it out immediately, see the naughty one, and you go and check immediately for the worst, and then you start to go down. At some point, the data starts to get better, and you know that everything below that is actually good data. So if you want to, instead of checking 700 brain, you can check probably 20, 30, and then you know that everything else will be fine because it's quantitative better than the one you already check. Okay, so this is something that you can use as well. And now, this is something that probably Ahmad didn't explain. This is an important key. When you organize your data, we kind of use a sort of PIDs organization. So you have your subject folder. Then you can have your anatomy folder, T1, whatever, but you definitely have to have a DWI folder with inside all the DWI in GZ, could be also me, doesn't have to be GZ, it's fine. Bival, Bivec, the reverse encoding, for example, the up, the down, the second direction for you, with again, nifty, Bival, Bivec. Even if it's only a B0, and if it doesn't give you the Bival and Bivec, you have to create it yourself. It's basically will be a file Bival with a 0 inside and a Bivec with a 000 inside. So then you might need to edit that sometime. But we can actually, maybe we can put some example online for people to see. At the end, you need to put this kind of acquisition parameters. This is actually from the FSL website, which tell the software essentially the phase encoding for the different volumes, for different scans. So there will be, I think it's down here. Yeah, you will have, for example, the first volume will be 0, 1, 0, say phase encoding is up, second is -1, means split down. The last number, 0 to 6, is the echo train length. Since you're not doing anything fancy, you're not using this pop-up to correct fMRI, you're just using for diffusion with diffusion, you don't have to know the actual real number. As long as you put that one, it's fine, because is in mathematics, what's happening is multiplying for this echo train length, and then it's dividing for the echo train length. So at the end, whatever you put in, it doesn't matter. Okay, this is useful only to have the right one only if you use the field map for another acquisition. So for the same acquisition, you just put it. This number is fine.
If you have one basic coding, if you just put 0, 1, 0 something.
If you have one, sorry.
Like one direction, basic coding direction.
Yes.
You only put 0, 1, 0 something. There's no.
Well, if you have 1, 0 direction, I'll come back to that, because we in the past we had another option called run all, run all top up. And run all essentially was doing everything except top up. But we now discourage that completely. You should do something for it anyway. So, and the solution using SymB0.
Yeah.
So essentially, you are going to have a folder somewhere with the T1, and the software automatically create a synthetic B0 undistorted from the T1, and then you're going to use this with the top up to generate the field mapping the same way. Okay. So if you don't have the reverse phase, you can use the T1 with SymB0. Okay, there might be some bugs to fix with that, because I'm using SymB0 manually, separate, so I do the field map by myself, but in theory, this script should be able to manage everything automatically, but I haven't tested heavily. So with time will be, okay, we can test and then you can complain with me. It's fine. Yeah, so as I said, when you want to, for example, here it is, here there are all the options, for example, this is a typical run subject, -F, beep, but all this one essentially is the meaning is -F, run the noisy and beeps ringing. -P is prepared for top up. B1 say just use one B0 per phase encoding. All the information are here. And again, you don't have to take notes now. Everything is on the website. So you just on the website, and you can use as a manual every time. Okay. As I said, in your case, for example, if you use the option -Y using SymB0 Disco or to generate reverse phase B0. Okay, so that's already included in the pipeline. Okay, so this is you let it run. It's gonna take some time. I don't know, 1 hour for my Mac to do everything from top up to edit. Depending on the computer, can be faster, can be slower. One patient, yeah. 1 hour, roughly is 1 hour. But because, as I said, some steps are not optimized. The thing is, the benefit, my suggestion, if you have a server, for example, with Linux and a GPU like a CUDA card, then half an hour, the hour will be done to 20 minutes. So this is because Mac doesn't have GPU that is compatible with CUDA, doesn't have NVIDIA card. So if you have an NVIDIA card with CUDA, it will be running much. In fact, the option actually to explain here, for example, you see I'm doing edit and -C0. Here I'm turning off the CUDA cards because I don't have the CUDA card in my laptop. Okay, but again, everything is written. My suggestion: don't memorize, don't learn this. Every time you want to do a process, just run all top up to you, and it'll give you the instructions. So you should, and you go and see which value you have to put. Just you see all the time, because I don't remember myself. There are different options. Okay. Okay, so how to install it? Direct installation. If you want to have probably the best, you install all the different requirements, which are ANS, FSL, and Tortoise 4.0. Okay, these are the, and you really need to we were gonna put this link if you want, but this is up to you. Okay, so ANS, FSL, and Tortoise, you need to install it yourself. If you, as I say, you are not confident with that, you don't like it, just go down and you have the Docker installation. And literally, when you have Docker installed, you open the terminal and you write this command and you're done. Okay, you just write this command, you specify where is your folder, where is your data, and that will be in the folder data. And you call this one bash, and you have a terminal with direct interaction, and you can call run all start away without installing anything because it's everything inside the Docker. It should work also with macOS, but because macOS is a completely different architecture, maybe a little bit slower. So that's why I'm saying I prefer for Mac to install directly, but everything else should be fine. I think I kind of cover everything. Any questions so far? Good. So at the end of the day, when you're all sorted, it's one command: run all, it's number of subject, and all the options that what you want to do. Yes.
For the multi-shell data?
Yes.
Where is that?
Yep, exactly the same. And also, I can tell you here, if you go here, for example, with Michelle now, we're analyzing a long scan, we did it 5 times. So we have 10 volume. So up, down, up, down, up, down, up, down. You just put up, down, all the volume correctly. And the concatenation will be based on the lexicographic order, based on the name. So you can potentially put the A, B, C, D. So if you want to keep an order, or 1, 2, 3, 4. And the only thing is, if you have 10 volume, 10 scans, you need to have an acquisition parameter 10 line. That's the only thing you need to know. That's it. If there are multi-shell inside, it will take care of it automatically. You automatically detect the number of shell and do everything fine. So this is there is no problem for the multi-shell. Okay? Right. So this was to give you more information about how to set up the preprocessing. And we've been working with this a long time, and everyone was asking us to do the preprocessing. Now you can do by yourself. No, it's working. It's working. So we crashed it many times, and now I think it's quite stable. Right. So this was one thing I wanted to talk about. The other thing I want to talk about is about this. I can do a demo if you want, but maybe it's not necessary. Let's see. So Startrack. So I think we already showed this slide at the time, but I don't think it's important. I put it here for another workshop. But just to people was asking why high B value is, as you can see, the sharpness of the angular information clearly increased with high B value. B3000, you have more information to resolve crossing, while low B value, everything is much smoother. And you see that low B value blurry, high B value sharper. But here how Startrack looks like. So it's a very low contrast, like but is a single table, is a single screen, and in theory on this screen you have all the options you want to set up your analysis. So you don't have to open anything. There is nothing in it. Everything is on the screen. You select. You want to do a single subject. You want to do multiple subject. Nifty. You can potentially even open data from Explode.ti if you want, but mostly it's Nifty. TRK, we don't do at the moment any export to Explode.ti. Here you specify in this is the general setting. Data source, you specify where is your file or where is your folder if you want to analyze multiple data set in one go. So you don't have to specify each Nifty file value, you just say the folder where all the data is. So as long as you have subject.ni, subject underscore mask, subject.bval.bvec, and all the subjects and folder is going to batch analyze all the subject in the same folder. So, and you're going to create like embeds multiple subfolder for each subject when the more it goes ahead. Okay. Then you have something to specify the modeling. For example, you want to make sure your gradient table are matched with your data. You know, normally the correct setting is always invert X because the data from the scanner is radiological order, so left to right, right to left. So I just want people to realize that. So I prefer to people to do that intentionally. You have to do invert X all the time. Then you choose if you want to do DTI, spherical deconvolution. Spherical deconvolution we can choose. I think we are going to explain more later, but you can explain if you want to do just the big shell, just two shell, you have different options. And here you have the parameter for spherical deconvolution. And at the end, these are the parameters. So data management, modeling of the diffusion model, and cartography. That's it. That's what you only need to do. So you set up the 3-step and you run it. If you want to disable cartography, you untick this. If you want to disable modeling, you untick this. But if you don't have the model, cartography say, I don't have a model, so I'm crashing. So yeah, it's going to tell you, please compute the model first. But you don't have to recompute the model every time. So you can just compute the spherical deconvolution once, and then you can do multiple cartography with different settings without redoing every time the spherical deconvolution. Okay, that's the idea. That was the example too. If you want to invert, why you want to invert the gradient, so usually invert X, you want to get the right corpo callosum, okay? So that's my suggestion is always start with a healthy subject, possibly not someone with a agenesis of corpo callosum, because otherwise you're going to be in trouble. But yeah, if you see the right corpo callosum with just a sagittal slice in the middle, and you see the typical shape, means that your all setting are okay. And this will be okay for all the other data set, all the other subjects. It's not that you have to do for every subject as well. This is you do once pretty much in your life, and every time all the subjects coming from the same scanner will keep the same setting. For DTI, we have a few models. We have linear. This is the simplest one that is, for example, in FSL and other methods. Weighted linearly square, a little bit more robust to noises. The best one is non-linearly square. Take a little bit longer. So this one probably takes few seconds to do the whole break. This is going to take a couple of minutes maximum. So it's still fairly fast. And this is a free elimination water. So if you want to separate edema from the standard DTI, so it's kind of already microstructure modeling, the simplest one possible. So you still give you the standard DTI. Well, the DTI with the dry up brain. So the mean diffusivity will basically didn't show any fast diffusion component. The mean diffusivity normally 0.6, 0.7. With the free water, the mean diffusivity go down to 0.3, 0.4. And you also have another map that will give you the volume fraction of free water. So if you want to quantify edema or water in the parenchyma, whatever, that could be a nice map to use. And that's how it works. So you set up, for example, your let's say we do a single subject, you set up this, we say DTI, weighted linear square, you set up, I say FA 0.15, 30 degrees, run. Literally, you get some information on your terminal, and then you open Startrack and you're ready to go for your dissection. So the data you have found in here is just being computed like that. For spherical deconvolution, it's exactly the same thing. You just select the spherical deconvolution option, and here you have the option, as I said, to choose just the top shell, the top two shell, or the whole shell of the dataset. My suggestion, always stay with the top shell, because when you do tractography, you want the best, the highest B value to resolve crossing. If you remember the beginning, I showed the image, okay? Now, which parameter you use for spherical deconvolution? Well, there is a nice button here called Calibrate SD, and it open a viewer, very simple view. Don't think about it like FSLI is. It's just a viewer that display a little bit of the brain. You can play around with all the different settings you want, and is also telling you, for example, this dataset at 3 shell, the maximum B value is 2500, 25B0, 2x2x2, and 207 volume. And for example, you can create a region of interest here and play around with different settings until you get a nice FOD field. For example, here in the corona radiata, you can actually see nicely. So you want to see crossing. If you get potatoes, you know, there's something's wrong. Tell you, for example, if you have a B500 and you don't see crossing, that means there is no point to do spherical convolution, okay? You have to have very sharp peaks, and anatomically they should make sense, because again, here, for example, you can play around with the invert X and do the wrong orientation, you're going to get wrong probability. So this is also a way to double check that your the gradient table are correct. Last thing is the threshold sphere here and down here, so we're going to see that, is essentially the threshold you're going to use for your tractography. Okay, so in a tractography with FA, with DTI, people say FA 0.15 or 0.2 as a rule of thumb. But if you want to do a tractography with spherical deconvolution, you have a HMOA or upper fiber density as a threshold. So we only track, or we do propagate until there is enough fiber density in the direction. So if you put the sphere, you can actually see this is my threshold for photography. Everything bigger than this sphere would be used for tracking. Everything smaller, my photography will stop. So you can actually see that pretty much most of the orientation are fine, but when you go in gray matter, for example, mostly will stop, which is this. And just to let you know, 0.02, 25, 0.03 are kind of always the value we always keep for pretty much all the value in vivo. If you go ex vivo or animal model, is another story, but for in vivo, 0.025 is kind of the standard. But yeah, this is already, you have an idea. You can always double check what you're doing with your photography threshold. That's the main point of it. Nice. Question? No. Right. Photography algorithm. This is just to explain the difference between deterministic and probabilistic, just so I have an idea, again, what you're doing. So when you do deterministic, your FOD are converted in vector fields. So each voxel have multiple directions we can pick for the photography. The way it's working is that we arrive here in this voxel. The voxel is easy because there is one direction, so we do another step. But now we are here, and now which one we are picking as a direction to follow? So there are different opinions. There is no right and wrong. There are different ideas of photography, okay? The most common choice, and the one we also follow, is to keep, we want to smooth change of direction, and we don't want sharp change of direction. So the idea is to pick the direction with the least curvature, okay? So how we do that? So we also have a search cone, okay? This is the angle threshold we use in the photography analysis. We want 45 degrees. That's the 45 degrees. And we say, okay, all the direction within this cone are going to conserve. Everything else is being discarded. So essentially, you see, now we have only one direction per voxel. And we interpolate like a DTI, and we do the next step. And that's your deterministic. So at each step, we look what is the neighborhood that is coherent with my trajectory. So we're looking for smooth change of trajectory. And usually it's worked well. Where it's not worked well is, for example, in projection system, when you have a fanning structure like corticospinal tract, corticothalamic. In that case, it's probably better to use probabilistic because by default they are biased to fan up anyway. So it's good to have this kind of. But if you want smooth and compact track, this is the best option. Okay, probabilistic. Again, probabilistic is exactly the same. As I said, when you have run, for example, deterministic photography, you can unclick this one. You don't have to model it again. And you can choose, for example, probabilistic algorithm. 20 runs means that for each voxel in the brain, we start 20 streamline because we want multiple repetition of the same voxel. And as you can see here, we increase the angle threshold because it's very noisy. The probabilistic is going to fan a lot. So what you want to control a little bit the angle threshold. So for example, 20 degrees is a good angle. For probabilistic, 20 degrees is what you want. And a threshold, absolute threshold 0.03 or 0.035, because essentially you will see it tend to go almost everywhere. So you want to kind of constrain, limit where it's going. And the probabilistic photography is very simple. If you read the chapter on probabilistic photography in the book, within the book we published, we introduce a new way of this classifying probabilistic algorithm. There is what we call dispersion tractography and real probabilistic tractography. The real probabilistic tractography is the one from, I don't know, Bedpost X, FSL, or I don't know. Some people in San Francisco using cue ball with the residual bootstrapping. So the idea is to use noise to see what is the uncertainty. But if you use spherical convolution and you use MR-Trix or Startrack, you can actually use the shape of the FOD as an anatomical information of the track dispersion. So the shape of this one is just how fanning is the track. So if you have a fanning fiber, it will be very open. If you're more pointing coherent, it will be more pointy. So the idea we use this shape as a distribution to pick up to sample our random propagation. And I don't know, yeah, you can see that. So clearly the peak would be picked up multiple times, while the more peripheral direction would be less. And that is essentially the probabilistic algorithm. Okay? Now, one warning, and then I finished. Some classical way of doing probabilistic photography is to run each voxel, I don't know, each seed for 2,000, 3,000 seed, a lot. If you try to do whole brain photography probabilistic with 1,000 seed, you're going to get a TRK file of more than 100 gigabyte. So you're going to kill your laptop or server, whatever. So don't do that, please. Okay. So if you want to do probabilistic like in the heavy hardcore probabilistic with like parser to parser, remember to use the seed. So you can actually see stratigraphy in one small region. For example, I want to do the dopaminergic system. I just do the VTA, substantia nigra, something, or maybe the striatum, and I see only from there, and I do 5,000 streamline from there per voxel. Okay, in that case, it works well. Okay, so but I told you, don't go whole brain with 2,000 streamline. Otherwise, don't come to me complaining for your computer. And that's it. That was a kind of overview. Is it clear? Do you want to see a practical demo to do that? Okay, fine. Yeah, I was hoping to. No. Right. Look, there's this one. Where is Startrack? Is it open? Should have it somewhere. Where are you? Oh, I see. Okay. So let me actually shut it down and restart from scratch. So we see if how it works. Okay. So to terminate and everything crash. Boom. Okay. So new Windows. Sure. Yeah. Yes. So let me explain the general. You have to keep this in mind. There are three major steps. 4. You convert your DICOM to Nifty. First step. Second step is pre-processing. So blip up, blip down, denoising, eddy current. This is kind of the same. MBL tools. This is using MBL tools, the one that I showed at the beginning. The Docker and the stuff. So run all. That's the pre-processing. Okay. Now with if you look at what's the name? Preterm or babies neonatal. Is a challenging data set because there is a lot of movement and things like so. You need to probably fine tune, make sure that your data is you might be if the data is really corrupt or motion, you might want to remove already manually the worst one because you know you're not going to recover them anyway. And then you look already with the data set is more manageable because if it's mess, the preprocessing is not doing miracles. Just get confused and get error. Okay. After you have done that, when you have, let's say you have done your preprocessing, you have a Nifty, Bival, and Bivec, and a mask. The preprocessing also give you a mask. You open Startrack and you do all your map, all your cartography, like anything normal. That's absolutely no difference or anything. And then after you've done this with Startrack, you open TrackVis and you do your dissection, or you open whatever tools you want to use for the cartography.
Yeah.
You sorry, I didn't understand.
Yeah, I mean, I don't remember.
You need to dissect. You need to do dissection with TrackVis to dissect. I mean, there are some tools to do automatic dissection. With MegaTrack, it could be a possibility to accelerate the dissection manually, but that is the thing. Okay, so let me see where I am because of software, I guess. Startrack, SD, Mac. Yep, okay. So let me actually get a bit bigger so you can actually see what I'm doing. Okay, so can you see here? Yeah, let me put it on the other side of the screen. So essentially what I've done, I just moved to the folder where this is installed. And there is a README file, a Startrack app, and a Startrack.sh. You just do sh Startrack, sh, done. And it's starting. It will take a few seconds because it's starting the runtime library. And here we go. We have a Startrack ready to go. Okay, let's try, for example, shall we do a little bit of a quick DTI? Okay, let's do a quick DTI. So you can just, let's say, with CD, like for example, I have no idea where to put the data, so I need to search at the same time. So let's say we go on Workshop 2025. data, and there is preproc. And for example, I will stop here and say open. So essentially, this is like SPM. You define where is the CD you're working on. And now you say single file. So load data nifty is very simple. You say, okay, the data is this one. Then load bval and bvec is this one. You just need to specify the bval because the bvec we assume is the same file name. So it's not a. And then load brain mask, you open the mask. That's it. The mask, as I said, is already created by the preprocessing and BL tools. Okay. So we have all the three files. So nifty, bval and bvec, and mask. And now we go here. I don't want to spend too much time. As I say, invert X, trust me. We can try, if you want, we can try to do it wrong and then we can see what's happened. But DTI, let's do weighted linearly square to just take a few seconds. Tractography, deterministic Euler. Let's do 0, 15, and 30 degrees, for example. And I want to do the runs is how many random seed are placed inside each voxer. So let's say 2, for example, okay? Run. And now you can see here, reading book, already computing the tensor, doing the tracking, and done. So now we open TrackVis. Open TrackVis, yeah. And we open it. Open track and scene, and I need to find it. Where is it? Preprocessing data, and it's this one. And this is your track. Done. Okay, and then you have also user. While you compute the tensor, we also save FM, diffusivity, etc. Right? Okay, so okay, I can go slowly. I've done so many times, sorry. I mean, you're not trying to do it at the same time, just following me, right? Okay. Okay. Right. So okay. So I'll do it again. So this is just to give you an idea of it. So let's try now. I don't know about the invert X. Let's say I do the wrong one. I say none. I press run again, and it's just redoing the same thing, computing the tensor. Everything looks normal. And then do tractography. Yeah, you already see something is odd because before we had, for example, where is it? 120,000 streamline. And now with the same setting, because the gradient are wrong, only 71. That usually is already tell you something didn't adapt, the propagation didn't work very well. So when this is done, you just, again, track this again, open. And you go in the same folder where you save it. And now let's see what's happened at this TRK. Open, and now it should be horrible. Yay. So now we open this one, invert. Now instead of visualizing the coronal view, we're going to visualize the sagittal. So remove the corona. And now you can clearly see something is really wrong with the corpus callosum now. See? Okay, so that means that the gradient table are not matching with my data set. Okay, so my idea, my suggestion is always get a reasonable, healthy subject, do preprocessing, see, turn around. Usually 99.9% of the time in vertex is the right orientation, but I don't know if you have a very old Philips or Siemens, they've done something weird. Even if you have maybe some post-mortem imaging or preclinical data where sometimes the orientation is completely weird, then you might need to play around to get the right anatomy. When this is fixed, so now we know that we get the right one, then, as I said, that is the same thing for all the setting. Spherical deconvolution is exactly the same. Is okay. It's already done. So one, I don't know if you saw replace track. One of the nice things of TrackVis is you can actually replace track. While I was talking, I already press again, generate again with the right option. And now if I go here, file, replace track, I can replace the new track with a good one. And now you will see, if it's not crashing, the right anatomy. You see, so much more. Okay. So this is the right. Okay, done. Now, exactly the same thing for spherical deconvolution. I'm not going to run. Oh, I can if I want. But do you have time? Yes, let's do it. So spherical deconvolution, I don't have to discuss again. We know the invert X is the same, so we'll keep it. Here you have the different option. I was saying max shell, two top shell, or all shells. This is because it really depends on your data. For HCP data, for example, you have a B2000, B3000. you can actually use the two top shells. So the one in option in the middle, because the B3000, who is calling me? So sorry. I'm sorry, it's really embarrassing, but something's vibrating in my pocket. So I don't know what is that. And okay, so max shell is when you, for example, you have a good SNR, you have enough direction, you can just take the top shell, for example, B3000. Take that, and it is enough. So all the edema, all the fast diffusion is suppressed, so that's all you need for photography. They don't say that specifically in MR-Trix, but that's what they're doing as well in MR-Trix. Essentially, the spherical, the photography, therefore the part is driven mostly by the top shell. In HCP, you have 2000, 3000. The 3000 is quite noisy, so it's good to actually combine the 2000 together just to give a little bit more data to analyze, and B2000 is also good enough, so you can do that. And if your data set is very noisy, or I don't know, you've done 30 direction or 2000, 30 direction or 1000, and you're desperate, you can use all of them if you want, but I'm not suggesting you should do that. You should get a better data. This is just for SNR and noise concern. So this is the last hope to use all the possible data to try to see something if it works, okay? But it's not the best option. So let's leave it this one. Alpha, yeah, this is one. This is usually the normal. Oh, you might want to write down this one because these are, don't ask me why, but these are now the standard setting for almost every B value, every number of direction. 0, 0, 15, and 16. This is kind of the standard value you want for almost every data set. That should be the new default, but I never had the time to just change the default. And then when you do stratigraphy, again, you can use, we say, for example, here, threshold 0.25 and 45 degrees is a good compromise, is a good general setting, okay? Right, well, I'll run it now. Oh, maybe not. Let me open this. I want to show you the calibrate first. So we open the calibrate, load me, and we open again the data set. I want to show you something pretty cool, bit geeky, but cool. Is this one, this one. Okay, now, for example, here, we can see that we have load the data, load the bival and bivac. When you have this kind of dot on, means that everything is fine. And I mean, we also loaded the gradient table, and now it's telling you everything about the data set. So voxel size, field of view, number B0, the maximum B value, number of shell. We go, for example, as I said, we go, for example, in coronal, we draw a ROI here. You do this, you do that. Usually you choose two opposite corners for it. It's a square region of interest, so you define the two opposite corners to a square. And then we say that we do invert X. Actually, let's do it wrong intentionally, none. And we do 15. As I say, you can play around with this. I suggest you to try intentionally to break it. So try different values so you understand what it means to play around with different fiber response, different regularization. So you understand, I mean, it's not, this is not making explode the computer. So you can just see what's happened, okay? But normally these are the normal value. They're working fine. Threshold sphere 002, for example, calculate FOD. And now it's going to generate this picture. And now you see something odd. You see, something is not adding because this is a corpus callosum. Where is it? Here, this is a corpus callosum. It's not actually building it's actually all in the reverse, right? This is again because we use the wrong invert axis. So the X and the Y, the plus X is minus Y. So everything is being flipped on the opposite side. If I do the right one, calculate, now it makes more sense anatomically. Okay, so you can compare the wrong one and the good one. Oops, sorry. The wrong one and a good one. And if you really want to explore the field of FODs, you can just rotate and see all the different, see how the literally in 3D, how the fiber are pointing. I mean, I always love to see this picture because each FOD is being computed independently, so they don't know who is nearby, and still you see how coherent, how harmonized are all the FOD, really showing the underlying anatomy. So we haven't done anything knowing about neighborhood. Okay, so that is when I'm happy with this setting, I just go back here, put a value for spherical convolution, put a value for topography, run, and you get the ST dataset you got in the workshop, in the things you did with Steffi before the other day. And I think that's it. Any question? Sorry, yeah.
Sorry. Have you talked about the algorithm? There is.
Oh yeah, good point. By default, now we all stick to Euler. It just gives a much smoother and more. It is the algorithm I explained before. At each step, we put the cone, we interpolate it. The MFACT is the older one, and is done by DSI Studio, one of the first DSI Studio or Diffusion toolkit many years ago, and is very robotic. So it doesn't change direction until you change the voxel. So each voxel keep straight, and then you change that. Is kind of, we just leave it there because some old publication use it. So if someone want to replicate, they can do that. But just use the ML layer for DTI or spherical convolution, that's fine.